Okay, our next presenter is Dr. Tom Sterling. Dr. Sterling has worked on a broad spectrum of pioneering computing projects. He is a co-author of 6 books and holds 6 patents. The topic of his talk today is, and let me look, towards the exascale, an arrow in flight. So let's welcome Dr. Sterling to the podium.
Thank you very much. And my thanks to John and all of their colleagues for the invitation. It's great to see many good friends and associates here once again in beautiful Newport. Sorry I missed yesterday. I was at the Department of Energy's SOS 17 meeting. You'll never guess what the topic was. Oh yes, big data. But just to show they were open-minded, it's big data in HPC. I'm going to give a presentation that's somewhat different than my norm. I'm not going to try to sell you on any idea. Therefore, I have very little experience at doing this, and I hope you'll be patient with me. But in fact, I'll slip a comment or two about my own work, but in a broader context. My role is very simple. I'd like to update you, brief you on what has been accomplished and the programs that are going on within the United States towards exascale computing. But without even touching a slide, I know there are many reasons why we care about big data. We have the smell of money, and there's, of course, the buzz phrase. Bill Blake from Cray gave the opening talk yesterday, and he put up the standard hype curve. And, you know, you just wait for those peaks to go by so you can get down to the real work. I'd like to just talk about the real work for just a second. I was just thinking, as Addison was discussing, and I really appreciate, Addison, your synopsis of the state of the field. I was just thinking about HPC and its processing of data and things that we've gotten out of this. When I was a child, and don't ask when that was, but I had a natural history book, and in the back of it was about a dozen pages on astronomy, and that was very exciting for me. And I remember, you know, working out the words and realizing the planet Saturn had 9 moons. If you go to Wikipedia, you'll find it's about 62, but I haven't looked in several weeks. It may be more than that. A lot has happened in a single lifetime, but let me tell you what has really happened in a single lifetime. I want to cite briefly 4 episodes, all of which has to do with high-performance computing, working on observed data. They all have to do with astronomy, and they all have changed in a single lifetime our view of ourselves and our universe. So, not quite 20 years ago, data analysis of the velocities of stars on the edges of galaxies were computed. And much to everyone's surprise, they weren't going slow enough. And from that, leaping ahead, was the discovery of about 27% of the entire universe. Not in space, but in mass. This was dark matter. About a dozen years ago, and for this piece of work, Nobel Prize was given, studying at the edge of the known universe, or as far back in time as possible, scientists, including but not limited to scientists of Berkeley, were examining, I think it's not that one should care, type 1a supernovas. And found, oops, well, they wanted to answer the question, how quickly is the universe slowing down in its expansion? And their great discovery, for which they got the Nobel Prize, was wrong question. When you've got the wrong question, you're really learning something. What they found, of course, is that the universe is speeding up in its expansion. Oh, and in the process of that, they discovered another 68% of the entire universe content. Okay, 68. So just if you're doing the numbers, we've come up with about 95% of the universe was discovered by high-performance computing processing data. 4.9% is, of course, everything we have any experience with, that we trip over, that we look at, that we blind our eyes to, 4.9%. Now, more recently, and by recently I mean within the last year, computers analyzing the data from what is truly an extraordinary piece of equipment, the Large Hadron Collider at CERN in Europe, have reinforced our standard model of quantum mechanics and therefore of the laws of the universe, and to all intents and purposes, though there's much still to be learned, prove the theory of the Higgs boson, that putative particle that lends mass to all other matter. And finally, for those of you who have just tuned in news in the last couple of weeks, high-performance computers studying data from yet another sensor source. This is a European Space Agency satellite producing the most accurate to date review of the background radiation, which is about 370 to 380,000 years only after the Big Bang, has found out that we suddenly got over 100 million years older. Instead, I woke up Christmas morning and the universe was 13.7 billion years old. But no more. It's now, you can write this down, 13.82 billion years old. Just, I feel older. Point. There are a lot of things we do with high-performance computing, and a lot of those things have to do with the way we manipulate data against models to give us understanding. Last year, we were really talking about clouds a lot. And the year before that, it was GPUs. Now, these have long tails. We are such a fast-changing discipline that we sometimes have to focus on one thing after another and then sort of forget, because we can't focus on three things at once. We can't keep all the balls in the air. All right. One of the things is the extraordinary rapid change of technology. And the closed loop in which we monitor or watch the technology change, we call it Moore's Law, and then we force a technology change in order to sustain that level of growth that we anticipate from Moore's Law. So to say it's a self-fulfilling prophecy is perhaps a little bit of an exaggeration, but there is a strong feedback. What I'd like to discuss over the next 20 or so minutes is the activities going on that will push us towards an admittedly arbitrary a milestone, however we measure that milestone, of exascale computing. We avoid exaflops computing. But recognize as, and I think Addison did say this, that we are in the midst of a revolution, and we're in a period, a transition period, in which there is great uncertainty, but also great excitement. So, briefly, the achievement of exascale computing will demand a change of methodology and modalities by which we both design and use future machines sometime around the end or the beginning of at the end of this decade or beginning of the next decade. We understand that issues of power and reliability have now come to the forefront, though they've been with us for decades, depending on specific applications. And along with performance itself, a product of efficiency and scalability, are now requiring rapid pushes in the change in which we structure these machines. And we understand, for example, that clock rate talked about earlier is not going up significantly. It will probably, for conventional systems, not exceed 3 gigahertz. So we're in the 2.3, 2.2, 2.7 area. Yes, Power 7 was well over 3.5 or more gigahertz. But we find that the trade-offs, especially where we can't even keep all of our logic busy on a die, hence the notion of dark silicon, it's better spent in different organizations and different combinations. So efficiency is both about energy and utilization or performance. And exascale computing has to find new levels in both of these. Yes, benchmarks provide in excess of 80% or 90% for MPPs. I'm not as enthusiastic as Addison is about the LINPACK benchmark. Not the benchmark itself. He's absolutely right. The data set is great, but the way we use it has, to some small degree, corrupted our field. This is understood, and we're moving away from that. we'll be moving back towards the kind of machine that our friend Gao just talked about, and to a more global address-based machine. Not out of desire for elegance or beauty, but out of a necessity of capturing the semantic abstractions in efficient ways of data access across global systems. This will become more necessary rather than less. And we are now going to probably move rapidly towards the use of runtime systems. Runtime systems have been around for a long time, but runtime systems towards efficiency and through parallelism discovery scalability in spite of the additional overhead costs. Now, the Department of Energy in the United States has taken over largely, but not exclusively, the responsibility of moving us towards exascale computing and beyond. Other agencies that care a great deal about this, of course, are the National Security Agency, which has its own needs. And believe me, if you want to talk to people who've been working big data, there's nothing new here. Or throwing away data, you talk to people at the fort. The Department of Energy has caused, within the last 1 to 3 years, new programs to attract attention and focus on the problem of achieving future machines and their use, and from different angles. So one of them, and the first one perhaps, is the co-design study that's currently ongoing. And this is looking at 3 different major classes of applications, areas, and these will seem suitable for the Department of Energy, in the areas of materials, in combustion, and in nuclear reactor design. All of these have long-term strategic, yes, mission-critical aspects to them for the Department of Energy. But both the problems and the computational techniques required have much larger scope of interest, not just within the DOE, but beyond and into the commercial framework. These are providing a set of complex problem drivers that will force the design process, is why it's called co-design, the design process of machine systems and programming models and ultimately architectures to support future computing. In order to help stimulate the vendors, the technology vendors, in moving the technologies not just where the cell phones are and where the enterprise server is, but where the technologies need to be in order to be doing exaflops per second. There is investment in a number, and you can see the list: Intel, AMD, NVIDIA, and WAM Cloud, which I believe got consumed by Intel through the early Fast Forward program. And this is ongoing as well. And it will be followed by another program that hopefully will invest more and more focused on these problems. Now, you might think, well, these companies are enormous. They don't, what does a few $1 million do for them? And in fact, in many cases, you would think they don't want the money because it detracts, it disrupts where their principal focus has to be. But in fact, the opportunity is in doing just those things that they could imagine in the longer term would be of value to them, but which is not on their short-term list. And so it's a partnership, really, between the government stimulating work and the vendors that's more than their short-term research goals. Perhaps the most significant and the newest, I think it's newest, project in the portfolio for the Exascale program under the Department of Energy is the Exascale program. This began last September and consists of 9 different projects, each with multiple partnerships. On your left are the large projects from Berkeley, from Intel, from Lawrence Livermore, and from Sandia National Laboratory, Degas, Trilica, DTEC, and Express. In these. There are 5 other smaller projects, including ETI and the University of Utah in compilation from Chicago, and 2 others. Frankly, I don't remember where Cal is from. That's terrible, I know. And Sleek. Each of these focus on a particular area, a particular opportunity. I'm going to focus just now on the larger projects and certain subsets of those projects. Now, this credit where credit is due. Almost all of these slides came from contributors within the programs. They're not my own. Some of them from Department of Energy, Office of Science, ASCR office as well. This and the previous one from Sonia Sachs at ASCR. And she is the program manager for the Exascale program. Now, the goal of the Exascale program is to, as the name suggests, look at the entire program hierarchy in software from the programming models all the way down to the lowest level interfaces to the architecture. And this cartoon gives a sense of the different approaches. For example, if you look on your left, you see there are multiple different user interfaces here, including the issues of MPI and MPI plus X, domain-specific languages, and new language concepts. Then you find in the middle or towards the right that with some compilation optimizations that are not necessarily being performed, we involve runtime systems. Again, except for the most shallow or limited way, runtime systems tend not to be employed because of their potential overhead costs in high-performance computing. What's missing here, all the way to the right, and for reasons I don't know, is the actual operating system itself. And operating system work is also being funded under the Exascale program, specifically under the Express project. Now, this is a timeline of hoped progress. The red line defines a critical time. And everyone in this room has to be very sensitive to the issues of government spending, government funding at this time. And there's great uncertainty, as we all know. There was a time when I didn't know what the word sequestration means. Now I don't know what the word sequestration is going to mean, but we're all going to find out in the next few weeks and months. Everything I'm talking about precedes 2014, not just because of the standard causal problems, but because it is building up to 2014, where ultimately the Department of Energy in the U.S. hopes to engage in something called the Exascale Computing Initiative. And this is the body of multiple programs that will together provide the full weight of the necessary sponsorship in order to move us. Let me make a side comment, because I don't have a slide on this. There are really going to be, or likely to be, two general classes of exascale computers. And this won't surprise you, probably. One is really an extension, as far as we can pull it, of the conventional practices that we're seeing right now. The issue of multi-core potentially combined with and integrated with some form of accelerators, although hopefully not in exactly the configurations we're experiencing currently, will continue to be pulled out. And where the problems are relatively loosely coupled, regular, uniform, and static in their allocations, we would anticipate continued success and progress in running legacy codes on such machines. And the first exascale machine, which will all likelihood be determined by the LINPACK or high-performance LINPACK benchmark, will probably be sometime in the 2018-2019 timeframe, not necessarily in the U.S., and it will look a lot like what we have now. And the reason is simple. Roadmaps are being put into place. Machine designs are already being formulated, and markets are being defined. And there are problem sets and software stacks with which the community has been successful to some degree. Having said that, it must be understood that as we increase the scale of these problems, we find more and more that they become more specialized. There are more and more problems that, using conventional practices, simply are not continuing to scale. These are strong scale problems, problems that take weeks or even months to execute a single solution, but which can only use a few hundred or few thousand cores. While today, the largest machines are between 1 million and 2 million cores, and that will continue to grow exponentially, and it's certainly been growing since 2005. There are many issues related to programming, to exascale programming, and they are really redefining the relationship between the programmer and the underlying machine and the system software in between. Do we continue with the software programmer, the application programmer, establishing exactly the layout of data and the tasks statically on each piece of hardware? Are we going to continue to have a first-name relationship? And when we find that we can't do that effectively, and we add X, where X may be, and most people would presume, OpenMP, there certainly works. So now I have two programming languages with which I'm doing, but We have any number of machines with GPUs. Many of those are NVIDIA boards. Do I then have to program my MPI with OpenMP calling CUDA? How many layers do we go before we decide maybe we don't have the programming language of the future, in spite of what many of our colleagues would like to believe? Nonetheless, that's exactly what at least experimenters are doing, and some problems are being crafted with relatively little confidence that that will be the future. The programming issues also ask, will the programmers be involved in energy management? Will they be involved in reliability management? Yes, we think petaflop machines are too hard to program, so let's make exascale machines harder. Fortunately, the Department of Energy, which is supporting that path, is also supporting a transitional path, a path that could be considered revolutionary by friends, disruptive by not friends, but are likely to define a second generation, a second class of machines, which will harness the technologies in the best way they can be, albeit at some cost to uniformity or legacy. Not the inability to run legacy codes. They'll run just fine. They won't run just best. There are a number of different interfaces that are being explored. These are only some of them that are being considered under the Exascale Program of Department of Energy. I'll say more about XPI because that's partly my own work in a moment. One emphasis that we see currently is on domain-specific languages. And the real virtue of DSLs, they can be fine-tuned to the needs of a particular application domain or computational methodology. The bad thing is that pretty much you need a DSL for every regime of execution work. But they're another hot topic, well, warm topic in any case. This is in part because the classic general purpose language simply isn't being perceived in all of its refinement at the moment by the community. Two other areas that are being pursued is Sketch from MIT, and this is a kind of language for pulling all the pieces together. So you'd say, well, wait, don't we have Perl? Don't we have Python? Yes, and this is a variation on that theme that allows us to pull pieces together, but are more cognizant of the problems of parallel and distributed execution. And Swift, similarly, at Argonne National Laboratories, is another kind of scripting language that allows composition of different pieces, because interoperability becomes really imperative as we try to hook new software with old software. Here's a table, and if it's a little bit sloppy in terms of format and fonts, it's hot off the press. This from our colleague Kathy Yellick at Berkeley pulled this together. You'll see a number of languages. I mentioned ETI's Swarm, and they have an interface called Scale. XPI, for some reason, we're already at the right. I really don't know what that means. But I'm going to point out a couple of others, including X10 and Habanera as we move forward. Okay, I guess I'm going to talk about my work. So why another computer language? You know, there are a number of things I never wanted to do in my career. I never wanted to be in the military. It was only 7 years. I never wanted to be a professor. It's been about 7 years. I never wanted to do a computer language. So it's about 2 years. XPI fills really a role that nobody wants to play, nobody wants to pretend in. It is a very low-level intermediate representation or intermediate form. It is certainly intended to be used to provide simply a stable abstraction on top of one of these runtime systems, or potentially more than one of these runtime systems, so that the applications work we can go forward with. It also is a target for source-to-source compilation from these higher-level languages like, but not limited to, DSLs. And for our particular purposes, it is a syntactic representation of an execution model called Parallax. I've spoken to you about Parallax in previous meetings, and I don't intend to do so, I think, in the next few minutes. XPI has a first specification, and the very thin piece of the software, which really does little more than library calls to the low-level runtime system, should be available sometime toward the latter part of this summer, and I think that that's actually a sane representation. So here are a number of the runtime systems. that we have the Exascale program is pursuing. Most of these had work under prior programs. For example, our program on HPX, a runtime system, the work on Swarm was done under the DARPA UHPC program, work done on, I'm looking for the X10 there. The X10 runtime system was done under the DARPA High Productivity Computing Systems program. Sorry, that was another 7 or 8 years. GasNet certainly goes back that long. I don't know what its original funding was. So there's leveraging of unique research ideas and being brought to make it useful. Here's, okay, that was terrible font. Therefore, let me give credit to Vivek Sarkar for this chart. Vivek is leading the Open Community Runtime System, which is intended to provide an early, stable, and widely accessible set of tools and interfaces in order to program next-generation machines, such as those based on Mike or Xeon Phi, with higher-level programming interfaces. It is less committed to any particular paradigm or model, but rather providing those mechanisms that appear to be of interest. GasNet is one of the first message-driven software packages that have been used for latency hiding by using a message-driven computation, which moves work to the data as well as data to the work, and emphasizes the PGAS, or Partition Global Address Space model. HPX is the runtime system under the Express project that uses lightweight threads with a form of message-driven computation parcels to provide high-efficiency latency hiding and increased amount of parallelism. It does so in a more sophisticated global address space called active global address space that allows virtual objects to move in physical space without changing their virtual name, something that's very important and something we don't do, and a very rich or powerful synchronization objects from prior art, but that generally is not integrated in standard models. And I think I've just touched on all of these, so I will let this go. HPX3 was developed at Louisiana State University, and under the Exascale program is being done at a combination of, again, LSU on the threads model, Sandia on the global address space, and Indiana University on the parcels and communication and synchronization. Here's a diagram of the X10 runtime stack. Now, X10 has many of these characteristics. It's both a language and a programming interface and a runtime system, and it has evolved substantially. Over the time, it's had more years to work at this. And so there's a significant similarity between this, and X10 is being used by 2 of the large programs, the Intel program, also the program out of Livermore that Dan Quinlan is running. Let me jump ahead. I think I've touched on all that. So this gives you a sense of the overall OpenX software architecture that many different projects are contributing to. You'll notice the operating system, the interface with the runtime system. That interface, that relationship is going to change. Here you have a case where the runtime system will serve the operating system as much as historically the operating system has served the runtime system. And that operating system is likely to be lightweight kernel. Whether it's a hierarchical operating system such as you find on the Blue Gene machines, or a flat set of lightweight kernels such as you found on Red Storm, is yet to be determined. I'm guessing it's going to be the latter, using a runtime system for global behavior, but really that's outside of the scope of improvements. Oh, okay, I knew I had a slide on Parallax. So Parallax Classic, if you'll permit the expression, which I have described here before, has the features that we've just discussed. But there's an area in which it does not adequately support the future requirements of computing. And these are in the area of locality management and the ability to have variable policies for task scheduling prioritization. And these actually need to be, because of the dynamic and adaptive nature of future computing, have to be part of the model of the computation, as well as the various elements that are used to implement it. And so Parallax is being extended currently to include locality management and scheduling policies for scheduling. And this is within the Express project, gives you a layout. There are 8 different institutions which are involved, academic, industry, and this is led by Sandia National Lab with strong support from Oak Ridge National Lab as well. And I'm done. I want to thank you very much for your attention, and enjoy the rest of the conference and lunch.